was that we were talking about a mean field theory. So the free energy, so-called Ginzburg-Landau. ওটা ইয়ে করতে হবে, অ্যাঙ্গেল জোন করতে হবে। We were talking about. So FGL, let's say, in a d-dimensional space, so integrated over all space, and then it is A over 2 phi squared plus half grad phi squared plus lambda over 4 phi 4. This is for a scalar phi. The vector phi, if phi is a vector having components phi 1 to phi n, then phi squared is phi I, and phi fourth is phi I squared. So that's the your phi square square. So that is the ON symmetry, isotropic in the phi space. So that, and the grad phi square is this chap over here, is del J phi I, del J phi I. So that's the scalar coming from the gradient of phi, and so, and if it is n vector phi in a d-dimensional space, then the j over here runs from 1 to d, the phi over here I runs from 1 to n, and j runs from 1 to d. So that's the we will be, I mean, for the most part, talking about a scalar field. The difference between scalar and vector field would depend, as you will see, on just the combinatorics of the diagrams. So that was the free energy functional, and the point was to calculate the partition function, which is a functional integral over all phi e to the power minus integral ddx of all this. So that's the task. Once I have the partition function, I can calculate all the thermodynamic quantities. So that's that. In particular, M, the magnetization, is the average of F of phi integrated over all space, and the susceptibility, zero field susceptibility, is integral phi x1 phi x2 or xy, as if you want. Then it is dx1 dx2. This quantity translational invariance means that it depends only on x1 minus x2. So the other goes into a volume. So the susceptibility is extensive quantity. And that's that. M is extensive, the ddx would give you a volume. Susceptibility del m del h is extensive, volume comes from there. So all that in good order. Then, all right, we started on the mean field theory, where what we do is replace a phi. So mean field theories replace phi by the expectation value phi, which is equal to m. So that doing that integration is not a that is, the free energy functional becomes trivial, F is equal to the volume. So F per unit volume is simply going to be A over 2 phi square, and this term is not there, plus lambda over 4 phi 4 minus H phi. So external field is H. And that is where we saw that we calculated the, so A, right, is A0 some constant times T minus Tc. So that allows the free energy to change form. The zero field free energy goes from looking like this to looking like this. So T greater than Tc, T less than Tc. So here you have this magnetization m square proportional to minus A, and that's what which is proportional to Tc minus T. So m proportional to that. Then we found the susceptibility. The susceptibility, which was del m del h going to 0, is 1 over T minus Tc above, and is 1 over 2 times Tc minus T below. So that's alpha beta and T equal to Tc, where the free energy is more flat at the bottom. You get m is proportional to h to the power 1 by 3. Finally, the thing which I did not have time the other day, what is the specific heat? What is the specific heat in this model? So if you want to get the specific heat, what you need to use is C is equal to minus T del to F del T square. And so T greater than Tc. So specific heat at constant field, which is 0, T greater than Tc, your m mean field, so m is equal to 0, and the specific heat is 0. Now, mind you, what is specific heat can't be 0. Why? What is coming out is 0 is the contribution of this free energy to the specific heat. The non-critical specific heat is always there. That, I mean, for example, if it is a gas, there would be 5 by 2 R, or that is not being touched. That is always there. It is a question of what this free energy, this needs to be very clearly stated, that this is valid only near the critical point when the phi, which is the fluctuation in the magnetization, is a big quantity. So it is normally, it is all thermodynamic, and thermodynamics gives you answers near the critical point. So if this is temperature and here is Tc, what you have is that, if you remember this van der Waals business, the point was this, changing to this, but there was this intervening period when this is just going over to this. That is where the susceptibility becomes very big. There is a onset of order over here. All this rho minus rho gas minus rho liquid, which is the phi, is identically 0, and then it sets in slowly over here. And if you look at the fluid, there are regions of the fluid where it is gas-like, other where liquid-like, and so gas, liquid, where all that's a fluctuation. Some region in space, and then a little later, maybe this is liquid, this is gas, and so there is fluctuation, which has time dependence, which has space dependence, and the question is, how much do these fluctuations contribute to the thermodynamic quantities? And that is being described through this over here. The non-standard, non-fluctuating parts are always there. So when I say that this is C equal to 0, it is just that the fluctuations are not contributing. If you have that 5 halves R or 7 halves R, that's always 3 by 2, 5 by 2, 7 by 2, have your pick. That's always there. So what about C and T less than TC? T less than TC, F is equal to now and A, which is minus mod A by 2 mm squared and plus lambda over 4 m to the power 4. The m square, which is the minimum value, which is m square is equal to mod A by lambda. That is the condition for the minimum. That is what it is over here. And so I put m square equal to that. And then it is minus A mod square over, I pick up 2 lambda over here, I pick up plus 4 lambda over here. So the answer is going to be minus mod A square over 4 lambda. So this is the free energy below. So that's, but then this is proportional to T minus Tc square. So if I look at the specific heat, which is this quantity over here, that specific heat is going to have a constant coming from over here. So del F, del 2F, del T square, that part is simply going, because this is T square, so this is going to be a constant with a minus sign over here makes it positive. So if I plot up the specific heat, this is against T, this is Tc, here is C. It looks like, I mean, you come like this and then it's like this. The important issue is not the going to 0 over here. All this is valid just in the vicinity over here. And what this is saying is that the specific heat will have a jump at T equal to Tc. So if you plot the specific heat, what this is telling you, that if I try to measure the specific heat, there would be the standard specific heat, which is like, let's say, atomic gas 5 by 2, or if it's a magnet, some kind of similar specific heat of some other. Come to Tc, what will happen is that if this comes up over here, when you go below Tc, just above Tc, it's somewhere over here, very little temperature dependence, then at Tc, there is this sudden spike. So that is what the mean field theory specific heat would look like. And actually it is interesting because there are lots of magnets which near the Curie point do show this finite jump. That is, the mean field theory is valid. Fluctuations are small, but there is a jump nonetheless, because the order does set in. And if the order sets in, you have a jump. Minus oh, this is thermodynamics, that specific heat at constant volume is T del S del T V. F is E minus Ts. So dF is equal to dE minus TdS minus SdT. This is minus PdV, and this is minus SdT. So del F del T at constant V is equal to minus S, and therefore it is T del S del T at constant V. S is del F del T at constant V. So this specific heat at constant volume is minus T. Where? Huh? Huh? Uh-huh.
So why lambda we are getting a specific picture, but we are not getting the specific picture.
That's a d equal to 1 model. There is no transition at finite temperature anyway. So d equal to 1, if you remember the 1D Ising solution, the specific heat at T equal to 0 is 0 as is required by none, and then actually looks like this actually. But I mean, that's the 1D exactly solvable.
Increase function is not 1D, but I will mention
2D specific heat is logarithmic. Diverges logarithmically. I mean, this, as I said, it's mean field where things are very muted. So that is small fluctuations. As soon as fluctuations become large, the specific heat is going to diverge. D equal to 2 Ising, it's logarithmically divergent at T equal to T square. Now, it turned out, I mean, this contribution, this fluctuation specific heat is 0 because M is equal to 0 above. So free energy is identically 0. So therefore, I mean, yeah. Mind you, the mean field theory is independent of spatial dimension. So the spatial dimension never entered the picture. So mean field theory gives the same answer in all spatial dimension. All right. So that's mean field theory finished. The specific heat has that was important to show. Now comes the question that why does one terminate a over 2 phi squared plus half grad phi squared plus lambda over 4 phi 4 and could have been mu over 6 phi to the power 6. Up down symmetry is being maintained, so I'm not then maybe some c over some 2 del square phi square, or things like phi square, right? I mean, all these could have been there. So offhand, what logic could one possibly use to say, I will ignore those and work with only this part of the thing? So I'll give you an argument which is correct up to a point and heuristic after that. So, all right. So, e to the power, your calculation is e to the power d phi e to the power minus ddx of all this. Anything in the exponential has to be dimensionless. Therefore, this quantity over here is dimensionless. Now, notice that I have deliberately kept the constant equal to 1 over here because I always have a free parameter. I mean, I could have put something over here, but then I would always be able to scale the phi so that this one becomes or phi or space, whichever take your pick, so that this, so therefore, I mean, yeah, because that's important, because now I know that every term is dimensionless. So I will find the dimension of phi in terms of the dimension of length. So units, that is. So here is phi, let's say phi dimension is like L to the power x. Then this tells me that L to the power 2x divided by L square times L to the power d is equal to L to the power 0. So this is 2x plus d minus 2 is equal to 0. So x is equal to 1 minus d by 2. So the dimension of phi is 1 minus d over 2. Now I need to find the dimension of A and lambda and all these mu, c, and so on and so forth, everything. So A and has some dimension, and then it is phi square, which is L to the power t minus 2 minus d plus d, that is equal to L to the power 0. So the dimension of A is equal to L to the power minus 2. So dimension of A is L to the power minus 2. Then comes lambda. So dimension of lambda, phi to the power 4, which is L to the power 4 minus 2d, L to the power d is L to the power 0. So dimension of lambda is equal to L to the power d minus 4. So lambda has the dimension L to the power d minus 4. Let's look at mu. Dimension of mu times dimension of this phi to the power 6, which is L to the power 1 minus d by 2 into 6 times L to the power d is L to the power 0. So dimension of mu is equal to, so this becomes 6 minus 3d plus 2d, which is L to the power 2d minus 6, right? Yeah. And 2d minus 6. 6, yes, 6, sure. So mu over here then is equal to and finally, let's do this one. Let's say, or whichever. No, let's do the other way. So see the grad square, so grad to del square, and therefore the dimension of C times this is 1 over L to the power minus 4, and then this is L to the power 1 minus d into 2, so it is 2 minus d, and then L to the power d is equal to L to the power 0. So dimension of C is equal to d's cancel out L square. Good. So we have the, yeah, good. L to the power. Yeah, good. So let's start with A. So there is this A has the dimension of 1 over L square. So it is proportional to some quantity which has a dimension of length in and the square of that inverse. Now, what in this problem is a dimension of length? Ising model tells you that it is the lattice size, right? I mean, that is typically in any problem. I mean, it is going, if it is a gas, it is essentially the distance of closest approach of the molecules. If it is, then it is the last, which is a small, very small quantity. So A, which would have to be inversely proportional to that small distance, is going to be large, right? Lambda is, so if D is less than 4, then lambda is going to be large. But if D is greater than 4, then it is different. C is always small. Mu is going to become big if D is less than 3. All right. So mu is big if D is less than 3, and so on. So if I'm sitting at D equal to 3, then I can't, I always have to keep. I can't do without. D equal to 3, lambda is important. Mu is just, this one is just marginal. And this is gone. So if I'm sitting at D equal to 3 and looking at this model over here, the terms that naively I would keep are this, this, and this. Because this coupling constant is big, this is also non-negligible. This one is just marginal, this one is safe. All right? So that, I mean, this argument, I mean, if I go to D equal to 2, everybody is important. I mean, not this one, but everybody else, D equal to 2, this is 2, this is 2, this, there is no difference between this and this. So D equal to 2, this is going to be a miserable model if I stop over here. But D equal to 3, I have some hope. So D equal to 3, therefore the mean field theory that one does is a reasonable answer at D equal to 3 is atrocious in D equal to 2 or 1. You still given, I mean, all right, this is for standard critical phenomena. When it comes to things like solid state models like Hubbard model, this and that, I mean, D equal to 2 can be, I mean, a mean field D equal to 2 theory there still makes sense simply because the fluctuations that you're talking about so on are very different there. Those are quantum creation annihilation operators. This argument has to be completely rethought. This is purely classical fields. Classical field, classical phase transition, and if it is classical phase transition, D less than 3, this kind of a model is not going to work. So all that you can, this mean field theory that we talked about is, I mean, truncating this and doing is a good starting point, provided, I mean, I'm at D equal to 3. So lower spatial dimensions, it would not be advisable to start with this over here. All right. So this Ginzburg, whenever you see in literature a Ginzburg-Landau model, you will never see terms like this. It's always this. And the tacit argument, which is not really spelled out, because all these dimensions are very clear. And the point is that this argument is also valid, turns out to be true when you handle the renormalization group. But all these things existed long before the mean field theory existed, long before the renormalization group. And they truncated it over there, but they never told you why. And the tacit thing is that you just do and you see that the spacing, relevant spacing, which will have to determine these coupling constants is small, and therefore this is always going to be big, and this is going to be small. So, all right. I mean, so that's mean field theory. যত dimension বাড়বে তত ভালো হবে. Absolutely. Absolutely. All right, but
সেটা তো স্যার L স্কয়ার এর চলে যাবে না, তো দ্যাট
4 এর
D=4 এর থেকে বেশি,
হ্যাঁ,
তাহলে ল্যাম্বডা যে ডিমেনশনটা আছে L টু দি পাওয়ার D-4 আছে,
হ্যাঁ,
4 এর থেকে যদি বেশি হয় এটা, তাহলে তো ওটা L স্কয়ার এর
ওটা আনইম্পর্টেন্ট হয়ে যাবে, ছোট হয়ে যাবে। So there, ওটাকেও বাদ দিয়ে the Gaussian model is going, হ্যাঁ, ওটাকেও বাদ দিয়ে। So the next, all right, so this is settled. Now this essentially lays the ground for why is Gaussian an important model. So f is going to be integral ddx a over 2 phi square plus half grad phi square plus lambda over 4 phi to the power 4. So and this if lambda equal to 0, which effectively is a good statement for d greater than 4, f is equal to integral ddx a over 2 phi squared plus half grad phi squared, and this is the so-called Gaussian model, and is exactly solvable, because that is exactly the integral that we learned how to do. So now you see that if we are close to d equal to 4, this lambda, suppose I'm in d equal to 3.9, lambda is not totally gone, but is small, and therefore a perturbation around the Gaussian model would become a perturbation in the spatial dimension, and therefore when you see the word epsilon expansion in critical phenomena, the epsilon is 4 minus d. So you use spatial dimension, you tune the spatial dimension to use it as a expansion parameter. The lambda will turn out is order of epsilon, and so the so-called epsilon expansion is a question of exploiting the fact that lambda is on the verge of becoming irrelevant as at d equal to 4. So that's yeah. Huh. No, it is not. But see, sometimes there's this thing that fortune favors the brave. So the point is that if you think that it is, you go ahead and do an expansion in order epsilon, and you find that if I just keep even the first term, I do significantly better than yeah, a typical thing which we will, I'm sure, that the susceptibility exponent chi goes like t minus tc to the power minus gamma, and if it's a scalar order parameter, the answer is gamma for n equal to 1, the scalar order is 1.246, so on and so forth. And mean field theory gives you 1. First order correction, gamma is 1 plus 0.16 epsilon. So that's a significant, I mean, it is picking up almost 2/3 of the whole. You go up to epsilon squared, you will come pretty close to 23 something. But these expansions, I mean, something catches up with you. They are only so-called asymptotic. They are not convergent expansions. And therefore, if you calculate the epsilon cube term, you go back. So the way of handling these, I mean, is that you now have to devise a trick for doing the highest orders. Can I have a trick for doing the high orders, and then you have a high order answer, you have a low order answer, and then you make a Padilla interpolation between the two, and you get it. So people do calculate these exponents to 7 or 8 decimal places, at least did in the 80s. Now it's not but it was a game which people played 30 years ago, or 30 to 3 or 4 decades ago, and you will get it. So anyway, so the technology of this remained, I mean, pervaded. Once this technology set in, it set in all across the different branches of physics. And but so far as the critical phenomena goes, well, I mean, you can. You wouldn't, I mean, that is, if you want to be extremely accurate, then the amount of labor that you would have to put in is enormous, which is also true for other problems. But then there the issue is that if you are looking at most of the other, I mean, as times change, you go on to a new field, and the experimental data that comes out is then sort of let's say new, in the sense, so it's approximations which you start seeing, not really. And then again, I mean, you switch on some expansion which is very similar to this, and you get a reasonable answer, and then you are off you go when things. And generally the thing has been that you learn the trick, and then you apply it to situations where things are, and then perturbation, and then one day the perturbation theory. If you are a high energy, there it is. The other way around is also very well established. This is the so-called weak coupling expansion, because it's the coupling constant is weak. The high energy people have something called strong coupling expansion, where you can have a technology for expanding in powers of 1 over the coupling constant, and that sets up now going between the. So if you can set up a high which over here the analog would be, if you have the time, that this is coming from around 4. It is possible, if this is a vector model, to come from d equal to 2. So that is with a scalar you can't, but with a vector you can. You can come from d equal to 2, and set up a perturbation theory. So you have something coming from d equal to 4, something coming from d equal to 2. And so anyway, all right, so that's it. But now we have to learn how to do how to manipulate this quantity. So what we have learned is how to do z. So z, which is d phi e to the power minus a by 2 phi square plus half grad phi square integral ddx is in terms of, so what we learned is that we do it in Fourier space, and so you use phi x equal to integral ddk over 2 pi to the power d e to the power I k dot x phi k, and this expression over here becomes a over 2 plus k square over 2 phi k phi minus k d dk over 2 pi to the power d, and the d phi is integral over all functions phi, so it is a pi of k and the d phi k and the d phi minus k. And we did this, and what we got was a string of quantities which are like 1 plus a square to the power square root of 1 plus a square, and infinite string running over all possible k's. And there were some constants which are not important, because you would always take a free energy would be the thing, so you get a minus kt log z, and therefore the constants come out as constants, and all thermodynamics come as derivatives, therefore that. So all right, so this is the only answer that so far that we know. K is not complex. K is real. So it is phi which is phi k which is complex, right? I mean, it is phi x is equal to integral ddk over 2 pi to the power d phi k e to the power I k dot x. K is real, but it is the phi of k which is complex because I have a I over it. Phi of x is real. Yeah, phi of x is. So you can, I mean, you can easily check that phi of k is found. Now write the inverse transform. So good. So I know how to do this. Now what? So I can write down the partition function. But what I need to do, I mean, what in this problem of the phase transition, my goal is to calculate susceptibility, specific heat, and magnetization. Quote unquote, magnetization is the expectation value, which can be a density difference. So those are the things that I want to calculate. Gaussian model has no phase transition, mind you, because there is no phi-4 term. Without the phi, as soon as A becomes negative, the model fails. So Gaussian model is defined if lambda is equal to 0, the model is defined valid for A greater than 0. So it's T greater than TC, you don't have a. So this, when it is a question of the Gaussian model, then I can't calculate the magnetization but I should be able to calculate the susceptibility and the specific heat. The susceptibility we found was chi is equal to integral the phi x phi y dx dy. This because of translational invariance. So this is volume, and this is let's call this a function gx minus y, and then it is d of x minus y. So g of n, which is let's say v integral gu du. So that's what the susceptibility is. I have to calculate gx minus y, which is the expectation value of phi x times phi y. So which is telling you that how is the field at point x related to the with the field at at y. So this is the correlation function. To be more precise, it's a 2-point correlation function, because there are two spatial points at which I'm looking at I could have been looking at other 3 points, 4 points, and so on. So this is, so I have to have a technology of calculating correlation functions, right? So I know I know how to calculate the partition function, but now I must have a technology for doing this, because unless I know that, I can't get the susceptibility. How to get the specific heat is another story, which will take so I can get rid of these for the time being. So how do I see calculating, as you have realized that in doing this, I changed to the Fourier space, which made life much simpler, because this whole concept of sum integrate over all possible functions, I could make sense of it in Fourier space, where I could say that it is just integrate over all phi k and all phi minus k. You will generate the entire set of functions phi. So I know the prescription, the meaning of this in terms of the Fourier space. Therefore, all calculations would be preferentially done in Fourier space. So instead of looking at this, one would like to look at what is it in the Fourier space. So I look at g of x minus y, which is equal to expectation. Now I put in the definition of the Fourier transform. So it is ddk1 2 pi to the power d phi k1 e to the power I k1 x dot product, but ddk2 over 2 pi to the power d phi k2 e to the power I k2 y. So this is equal to, so it's e to the power, so integral ddk1 by this, ddk2 by this, expectation value of phi k1, phi k2 and e to the power ik1x, e to the power ik2y, and then this is your g of xy, and which is phi x, phi y over here. All right. So now it's a question of having to talk about that what is this quantity. So g of x minus y is a function of x minus y over here, has to be such. If this is going to become a function of x minus y, then the only thing that you would be picking up is the situation where k1 is equal to minus k2. That is what would make this right hand side over here a function of x minus y. So this quantity over here, phi k1, phi k2, is some function. The statement that phi x, phi y is a function only of x minus y translates in the Fourier space as this is a function, some, let's call it some g of k1 and delta of k1 minus plus k2. Right? So it's g of k1, delta of k1 plus k2, and now you can do one of the integrations over here, which removes the delta function, makes this k2 a minus k1, and you have e to the power ik1 x minus y, and g of x minus y is equal to that. So the structure, this phi k1, phi k2, to give, in order that you get a g of x minus y over here, is g of k1 delta of k1 plus k2. So the only correlation function that is going to survive is the correlation function, which is phi k1, phi of minus k1. You can see it in another way. Let's say I actually have to calculate. How would I calculate phi k1, phi k2? That is from first principles. The first principle calculation would say that this expectation value has to be, it is, all expectation values are defined by that there is this probability distribution, this weight factor over here. I mean, this is what gives you the Z. Everything else is going to be expectation value. If I have somebody's expectation value, I put that in over here, evaluate that integral, divide by the Z. Right? That is the thing to do. So it is the Z, let me, as written down over here, looks like this over here and gives you this. So phi, imagine that I have to calculate the expectation value of phi k1, phi k2. If you ask me what is the expectation value of phi k1, that is equal to 0, because this is a even integral, even function over here. So phi k1 is equal to 0. Now it is phi k1, phi k2, and this is the weighting factor. Now you look at, if k1 is not equal to k2, then it is still 0, because the only relevant part which k1, let's say, is going to see is the phi k1, phi minus k1 over here. And therefore, I mean, it will give you 0. Similarly, the k2 by itself is also 0, average 5k. And that is going to survive only if K1 is equal to minus K2. That is when the answer, if K1 and K2 are not related by a delta function, the explicit form over here, which is do the integral pi d phi k pi of k d phi d minus k phi k1 phi k2. These are fixed numbers, e to the power minus summation k half a plus k square phi k phi minus k. So that is what you have to. This is the integral that you have to do. Now k1 and k2 are fixed. These are, I mean, and you are doing an integration over all this. So long as you do the integrals, all these integrals, all the k's are decoupled. All the k's are decoupled, and therefore, when k is not equal to k1 or k is not equal to k2, you just pick up this quantity with k not running over k1 and not running over k2. And then when it runs over k1 and k2, then it is going to be this. And if k1 and k2, then what am I looking at? I'm looking at phi k1, phi k2, e to the power minus a plus k square by 2, phi k1, k1, phi k minus k1, plus a similar thing with 1 going to 2. That is the integral I'm looking at. That is only what is, the others have just and given me this. The rest of it is simply, but k not equal to, k equal to k1 and k equal to 2, that part is going to be this. So that part is going to be this. And if now I look at this integral and this integral over here, integral over phi k1 is going to give you 0. And similarly for this one, the integral is going to give you 0. So the only time they can exist is if one is the negative of the other. So it is phi k1, phi minus k1, and what you have over here is that it is a plus k squared into phi k1, phi minus k1. So that is the part which is going to give you an answer which is everything is divided, expectation value, everything is divided by z. So all the non-K1, non-K2s have cancelled out from upstairs and downstairs. And it is in the, it is only for this K1 over here that it is different. And different how? In the sense that you have an extra phi k1, phi k minus k1 over here, which means that apart you are going to have an extra factor of 1 over a plus k squared. So this correlation function that we were talking about, this has to be equal to, this has to be equal to delta of k1 plus k2 divided by k1 squared plus a. That is the only new thing that has come. Everything else is another term of this kind. And they all cancel from top and bottom. The only only survivor is this 1 over a. Because here is, I mean, if you look at it as a two-dimensional integral, what you are looking at over here is like r dr, and you are looking at minus alpha r squared. So,
we are going flexible about that exponential minus that integral, that summation. So we are very flexible about it. How we are doing it?
What are we about it?
Sir, that exponent power that integral.
Huh.
EDK,
Huh.
we are converting that to a summation.
To a summation. So where is which summation? Because this integral is a summation, right? I mean, it is a the integral over here is a summation over e to the power minus integral of this. So this is over here. You have a summation over all case.
We have a summation, but over there, if it is the integral, key is continuous. But we are converting that to a summation. That means we are changing that.
Just imagine that doing on a lattice. Just imagine doing on a lattice. Yeah, you always imagine that you are doing it on a lattice and then take the lattice spacing going to 0. So discrete, to focus attention, do discrete, and then when nobody is looking, take the limit. That's and that's legal. I mean, there would be textbooks which would tell you exactly, I mean, why it is legal and so on and so forth. And you don't make a mistake by doing it. So this is the next big step, that you can calculate with the Gaussian weight function over here. You can calculate the z, which is equal to this. You can calculate phi k1, phi k2, which is equal to this. If it is 3 odd number of phi's, you will have 0. If it is even number, say it is phi k1, phi k2, phi k3, phi k4, this expectation value. Now you can see that it has to break up pairwise. I mean, you can either get phi k1, phi k2 times phi k3, phi k4, or you could go with this and this, or you could go, I mean, so this can go with this, or this, and would accordingly give you, break it up into 2 products over here. And it would not be 1, but it would be a sum over all the cycles that you. Right, yeah. You would get 1 and 3 and 2 and 4. 1 and 2, 3 and then yeah. Then so you get 3 of them, which phi k1, phi k2, phi k1, phi k3, phi k, which is the analog of for the Gaussian thing. This is 3. If x was a Gaussian distributed variable, x4 average is 3 times x square average whole square. The analog is that it is this over here. You get break up into 3 parts: k1, k2, k1, k. Yeah. So this is, if I have 2n of odd number, 0. Even number, it breaks up into strings of this kind, and you have to sum over all possible permutations of this, which is the analog of Wick's theorem in field theory, quantum field theory. All right. So if you, since you have had the QFT course, so this is the Gaussian analog of Wick's theorem. Yeah. So we are in business. There is. All right. So let's see. Where else can? What else can be? So all this was because I wanted to do the susceptibility. So now I have done this. The susceptibility was this question of calculating phi k1, phi k2, and we had to do integral, what was it? It is this chi k is the k is equal to essentially, this is the, yeah, and this is g of k1 k2, which is essentially gk, which is phi k phi minus k, this over here, and that's my g of xy. So that's my this the, and now I'm in the whole thing started with the susceptibility, which was the susceptibility which we did last time was this integral. Susceptibility was the expectation value phi x phi y dx dy. So that's the susceptibility, and this becomes equal to v times this phi x phi y d of x minus y, which is equal to the Green's function g at k equal to 0, right? So g of k, so g of x minus y is this quantity gk and k1 plus k2, and what you are looking at, the g of what one is interested in, is essentially the this better write down. Yeah. So this is where we are. I'm interested in g of x minus y, and then it is a question of d of x minus y. This integral, it is g of k e to the power I k dot x minus y d of x minus y integral over this over here, which is the, where am I? It's g of x minus y d of x, where am I? It is g of this, that's the Fourier transform. So I have to write gk e to the power g1 over here is ek e to the power, so k, it's, I'm writing the Fourier transform, so it is gk e to the power, so x minus y, let me call it u, so e to the power I k dot u, there is this du over here, there is the ddk coming from over here, and then you do the integral, which is gk ddk. I need to pick up the k equal to 0, so I'm looking at the susceptibility over here. I'm looking at g of x minus y, so I have got phi x y dx dy, which is the which should be the g of k equal to 0. So g of k is all right. I mean, trivial should have g of k equal to 0. G of k is equal to integral phi k e to the power. This is equal to g of k is the phi x phi y, which is this e to the power I k dot x minus y d of x minus y. That is by definition the g of k, which is, this is g of x, g of x minus y, phi x phi y e to the power I k dot x minus y. So g of k equal to 0 is phi a, this is 0, 1. So phi x phi y is this, so it is g of k equal to 0. So G of k equal to 0 is the susceptibility where through this argument over here, and now you have the G of k equal to 0. G of k is this quantity, so G of k equal to 0 is equal to 1 over A, and hence the susceptibility is proportional. 1. So Gaussian model, the susceptibility is T minus, because I can actually calculate the G of k. The G of k is given by this quantity over here. So that's the correlation function in Fourier space. G of k equal to 0 corresponds to the, so just integrate over x and y. So that gives me the k equal to 0 part of G, and that's equal to 1 over k. And so this is. So, all right. So G of x minus y has the Fourier transform here, this, and everything is done. Oh, all the D is all, I mean, these are, yeah, sure. So it's a spatial dimension goes. So that wrote it explicitly here. Should have, yeah. Operator. No, the operator is your del square phi plus del square minus A. That's the operator, or minus del square plus A. That's the operator. So if you want to think of it as an operator, then it is the operator of the minus Laplacian plus A. And if you think of it as a correlation function, which is much easier to do in this context, it is just what you see. All right, so that's the susceptibility. So susceptibility calculations would always go according to the technology for doing susceptibility calculations would be to calculate. So susceptibility, the takeaway from this is susceptibility, you calculate phi k. You calculate the 2-point correlation function phi k, phi minus k, and k equal to 0 gives phi. So that's the, if k not equal to 0, k not equal to 0, then you have the structure factor for scattering experiments. If it's a liquid, then it's light scattering. If it is magnet, then it is the neutron scattering. So k not equal, so you calculate this quantity over here. This quantity over here at finite k gives you one kind of information, which is non-thermodynamic. It has to do with the scattering amplitudes. And if you are at k equal to 0, it gives the thermodynamic quantity, which is the susceptibility. So these are the structure factors are more are close parallels of what would be scattering cross sections in the corresponding high energy calculations, and the thermodynamic thing is unique, obviously, to the StatMech system. So k equal to 0 gives you that. So that's the susceptibility. Then the other is the specific heat. So we are just setting up I mean, the technology, and then after finishing up the technology over here, we'll go back to doing icing and come back from there once again to see. So how am I doing on time is the issue. Another 10 minutes. Oh, very good. Let's can get started. All right. So specific heat. Gaussian model specific. Now, specific heat, see, susceptibility you got through the mean field. So you have a answer, so that is not so much of a surprise. The specific heat, we have done mean field theory, where it was gamma equal to 1. It was beta, we got beta equal to half, we got delta equal to 1/3, and we had what else? Well, alpha was alpha essentially 0, it's just a step. Gaussian. Alpha, beta, gamma, gamma equal to 1. So Gaussian, gamma equal to 1 once again. So gamma equal to 1 in Gaussian can't get a beta or a delta, because so beta and delta are not defined. So question is alpha, where the mean field theory did not make much headway. What about the specific heat? So Gaussian specific heat is actually non-trivial. So question is, how do I get the so A is equal to A0 T minus Tc. So the meaning of A is that is where the temperature enters the Landau-Ginzburg free energy has A equal to A0 T minus Tc, changes sign at T equal to below, and that is why the Gaussian, when I have thrown out the lambda phi 4, is not defined for T less than Tc. Good. But so T greater than Tc it does well. So what is the specific heat? Specific heat C is minus T del to free energy. This is the thermodynamic free energy. If I'm going to do this over here for this few minutes, let me put a, so F thermodynamic is equal to minus kT log Z. Z, the partition function is d phi, the functional integral e to the power minus this f over here. And then, so specific heat is this. So let me go back. This T over here is not important, because this T is, I will write it as T minus Tc plus Tc. So if it is this T minus Tc, then that term is automatically very small near Tc. So therefore that is of no interest to us. So this goes to minus Tc del to F del T square. For us, the only variable is T minus Tc. So if T minus Tc has to be there, and it is, things are going to be determined as a function of T minus Tc. T is, but it is, it's an easy analytic function. The whole business of this is that you are getting into answers which are non-analytic. even the mean field theory, giving you exponents like half and one third, telling you that analyticity is not the thermodynamic functions are not analytic at the critical point. So there is a therefore I want only the singular part, and therefore I replace this TC by this over here, and now del F del T square. This is all thermodynamic. I want to take a derivative with respect to A. So del T square is this. So I can write this as T minus TC. TC is a constant, and I can put a A0 over here. So this is minus A0 square TC del 2F thermodynamic divided by del A square. Now I'm ready to take a derivative. So F thermodynamic del F TH del A, which is going. So this is equal to. So now I can write minus KTC log Z, and this is equal to F. This is equal to minus KTC divided by Z del Z del A. All right, del Z del A. Z is this. I'm going to take a derivative. Your F is this. I'm going to take a derivative of Z with respect to A, which means that I'm going to bring down. So this tells me that del Z del A equals. So del Z del A. So it is e to the power minus f over here. So it is minus this. So there is going to be a minus sign, and it is a derivative. So it is a minus half, and what is going to come down is phi square x d dx. That is what comes down, and with a, and I still have the e to the power minus f. Right? So Z is equal to minus half phi squared ddx e to the power minus. So if I do one step, then I come over here, and the minus and the minus are taken care of through this, and so that becomes a plus. But I have to do another. All right. So now my question, that I have done one derivative. I have done one derivative. I have got this. So I know that this has become this quantity over here. If I take as another derivative, then what am I going to come up with? So I'm taking another derivative with respect to A. So all right, let me write down one step. A bit pressed for time. Let me write down one step, and meanwhile you figure out. Think about it, and let me just work out one step. It is 1 over Z del to Z del A square minus del Z right? So I have taken this minus k out, and that's that. All right. Del Z del A, I have already figured out. So this is this. Now you can easily see what del Z del A square is going to be. It is going to be one integral phi square x1 dx1, another integral phi square x2 d2. And divided by this z square over here. question is, what is all right, let me write down what.
I square whole square and 5 to the power
5 to the power?
4.
This one and
Square expectation value of I square x square.
And this
5 to the power 4 x.
close, yes, but there is no. You remember that there is a x. So how would I would have said yes to what you said, except that you have to note that I'm writing phi square x ddx. So how would you? Right. So what this would, all right. You can see what this term is. This term is, so half phi square x. So if I put a 1 over z over here, then I put a z over here, and what this becomes is a minus half and the expectation value of phi square dx. Right? So this part, this second part. So this second part over here is clear. It is 1 over. It is a square. That means, I mean, I pick up a square of this expectation value. And what is the first term? The first term is that it has to be phi square, phi x square, phi y square, dx dy, and then the expectation value, right? So that's what it is. So the specific heat, which is this, is equal to A0 squared divided by 4 and Tc, and then we would be having expectation value of phi square x1 ddx1, phi square x2 ddx2, this x minus expectation value of phi square x1 ddx1, this one square. So that's the specific. So this is the expression for the specific heat. It is nu these. There is phi square x1, no, phi square x2. And so I have to do a different kind of correlation. So you are now looking at, for the specific heat, a correlation which is like phi square x1, phi square x2. So susceptibility, you were interested in phi x1, phi x2. And over here now, it is phi square x1, phi square x2. So if I do all calculations are in Fourier space. So if so this is going to be integral with ddx1, ddx2. All calculations will be in Fourier space, so I have to go with this, and I would be picking up in this when I sum p phi p, and there would be some phi minus p, and there would be phi q, and there would be some phi minus q. In general, I mean, it would be phi p1, p2, p3, p4, delta function of p1 plus p2 plus p3 plus p4, which I mean is going to finally look like phi p, phi minus, and therefore you would factor, I mean, essentially that what we said, if I have 4 functions, then you break it up into a square of Gaussian integral for string of 4 is essentially string of 2 squared. Right? So it's Gaussian, and therefore, I mean, so essentially you would be having one factor of this kind, one factor of that kind, and then you square. So you would be, one has to be a little careful. The P's and Q's would not be, I mean, you wouldn't be totally, there are these integrations over ddx1, ddx2. So it is not that you are completely free and you have a dp and a dq integrated over. But the point is, there is going to be a 1 over p square plus a coming from over here, and a 1 over q square plus a, but there would be a delta function coming in which would essentially reduce it. You can give it a try, or else I mean, if we'll go over it next time, that I would be ending up with an integral which looks like there is a dd overall momenta, and it would be 1 over p square plus a whole square. So the specific heat in the Gaussian case is non-trivial. If it is d equal to 3, then you can easily see the answer, that the answer in d equal to 3 is 1 over square root of a. So the specific heat diverges at the critical point in the Gaussian model. That's a very strong answer. Specific heat does diverge, but very weakly. So not as the strong. So Gaussian model gets the specific heat divergence, but that is what I wanted to end with, is that the mean field showed no critical behavior. The Gaussian goes the absolute other way, shows a very strong critical behavior. It is qualitatively right in the sense that there is a critical divergence of the specific heat, but numerically it is not very good. So this is a good place to stop. You can try working out